Today I'd like to talk to you about heat transfer. The major idea with heat transfer is we're trying to figure out how rapidly energy is passing through a barrier between a hot object and a cold object. So we want to know how much energy is passing through the barrier per second. Sometimes we want to minimize how much energy we are losing. Sometimes we want to maximize the amount of energy we're using. So in the wintertime, we might want to minimize how much energy is passing through our jacket, our gloves, our hat. With our car, we want to get energy out of the engine as quick as possible to keep it from overheating. So we need to know what are the factors that are going to determine how much energy is passing through our barrier per second. Turns out there's 4 of them. The first factor is the thickness of the barrier. Thickness is going to go by the letter L, and we're going to measure it in meters. We studied this in lab, and we found that as thickness got larger, the rate of transfer got lower. Okay, so we could see at 36 millimeters, we had about 200 joules per second passing through our barrier. And we could see at about 8 millimeters, we had about 1,000 joules per second passing through our barrier. Remember that although it might be convenient to measure in millimeters or centimeters, you have to work in meters when you do your calculation. The next factor is area. That's going to go by capital A, and it's going to be measured in meters squared. I hope you can see that every square centimeter of area is another spot for heat to pass into the container of ice cream. So more area means more heat transfer. If I double the area, I double the amount of energy that's able to get into my ice cream. The next factor is difference in temperature. So my hand's going to be hot, maybe about 33 degrees Celsius. The ice cream's going to be cold, maybe 10 degrees, negative 10 degrees Celsius. The bigger that difference in temperature is, the quicker the heat is going to pass through the barrier. If my hand were cooler, not as much energy would be going into the ice cream. The material that I make the barrier out of is also very important. The letter we're going to use for the material is K, and it stands for conductivity constant. You will find a list of materials on one of your reference sheets, and it will tell you the conductivity constants. You might want to put the letter K on top of that column. Bigger numbers mean faster transfer. So if you want heat to go through the barrier quickly, you make it out of some kind of metal. If you want the heat to pass through more gradually, you want to use one of the better insulators, such as Owens Pink. Owens Pink is the stuff that you put in your attic. Sometimes you'll do it with rolls of insulation, and sometimes with little flakes that are blown onto the attic floor. Either way, it will help to limit the amount of conduction of energy through the ceiling of your house. You will see a substance called down. You might have a down jacket or a down comforter. Down is simply referring to the material inside the jacket or the comforter, and it turns out that it is feathers. Okay, so whenever you see down, that's your number, and please know the insulator is actually just feathers. You'll see argon and krypton gas. They are gases that might be found in your double pane windows at your house. You'll have 2 windows, and trapped in between will be a gas that is a very good insulator. So to summarize what we've done, there are 4 factors: thickness, which goes by the letter L, measured in meters. You want to have it really thick if you want to slow down the rate of heat transfer. You want it thin if you want to increase the rate of heat transfer. Okay, the next factor would be area. When you do area, you just do the area of the side in contact with the hot. Okay, so maybe you do width times height to get the area of that panel. And again, you want it in meters squared. You want the difference in temperature. Now watch this. This is something that you should know about. You can work in either Kelvin or Celsius and you'll get the exact same answer. So in Kelvin, if I do 305 minus 284, I'll get 21 Kelvin. If I do 32 Celsius minus 11, I will once again get 21. So either way, with delta T, you can be in Celsius or Kelvin, and you will get the exact same numeric answer. The final factor is the material, and that goes by the letter K. You find it on your reference sheet. The formula looks like this. Heat, that's going to be measured in joules. Time, that's measured in seconds. This is from your yellow sheet or maybe your green sheet, depending on which one you got. Area, meter squared. This can be in Celsius or Kelvin. This is thickness, and that's going to be in meters. Again, sometimes we want this to be a big number, and sometimes we want it to be a small number. Remember, joules per second can also be called watts. How does this transfer actually take place? So what you want to see is if we have a hot area and a cool area, what happens is the hot makes the molecules vibrate quicker. They then collide with their neighbors and transfer some energy. They then collide with their neighbors and speed them up and transfer some energy. And by way of a series of collisions, we move the energy from the hot side to the cold side. And again, the factors that determine how quickly: the material, the area, the difference in temperature, and how thick your barrier is. So hopefully you understand a little better about how heat can move from hot to cold and how we can calculate the rate at which the energy moves.